Hello and welcome back to the Hyperthesis. We're at episode 86, and today we have very interesting topic, I think, and also quite, the big news that just came out recently too. My name is Feely.
I'm Patrick.
And I'm Liam.
So I guess the first thing that we found out this week, which is gonna be our main topic, is the Nobel Prize in Physics got announced, and the Nobel Prize in Chemistry also was announced. So that's interesting. But before we get into that, there are space news that are quite interesting. The other day,
Lots of interesting things.
yeah, it's a good week for science overall. I heard the SpaceX caught their mega rocket basically, right? It looks like the little tongue that they just snatch it. That's really cool, and also it's like it looks like it's light, but it's thousands of tons, right? That's fascinating.
Yeah, this was incredible news and kind of jumped off nicely from our last episode where we ended with a whole bunch of news, especially space news. But SpaceX, as of yesterday, at the time of recording, really made some rocketry history with their Starship rocket. So before we get into what actually happened, I just want to provide a little bit of background with numbers. Because if you've seen any of the videos of the SpaceX rockets landing and the video from yesterday, which there are some incredible views, there's just something to keep in mind, and that's the scale of everything. So this was the fifth launch of Starship that happened, which is the Starship vessel itself is kind of like the second stage shuttle or reusable vehicle that holds all the payload. And that sits on top of what's known as the Super Heavy. And the Super Heavy is really what made history, but we'll get into that in just a minute. But Super Heavy is a liquid fuel booster that lifts the Starship from the ground. So they're attached together up and through the atmosphere, through the thickest part, and up towards the top of the atmosphere. Before they detach, the Starship goes on and it can orbit. There are plans to send it to the moon and possibly Mars. But once they detach, the Super Heavy then starts its descent back to Earth. And again, just to give you some numbers, so stacked on top of each other, they are 121 meters tall, or about the height of a 36-story building. So that's not even just like a low-rise or mid-rise. That's in some places considered like a high-rise building that's 9 meters in diameter.
Yeah. Also, for context too, the Statue of Liberty is only 93 meters, or about 300 feet, right? So the Starship with the booster, with the fuel tank, is taller than the Statue of Liberty, so it's quite large.
And it's also the largest rocket that's ever been made. So the Saturn V, which was the previous record holder for about 50 years, that one was 111 meters. So this one beats it by about 10 meters high. And the engines, of course, are more advanced. There's been 50, 60, 70 years of engineering done on rockets now. And so instead of having something that did get us to the moon, we have something even more powerful. And just even looking at the weights, it's insane. Like combined, these two pieces of the Starship rocket weigh 5 million kilograms, and they can carry between 100 to 250 metric tons, which is huge. So the Super Heavy alone, that's the first stage. So that's responsible for getting everything kind of out of the thickest part of the atmosphere and really giving a lot of kinetic energy to get it either out of the gravity well of Earth or orbiting, which requires quite high speeds. And this itself is about 71 meters tall and weighs 3,675 metric tons when loaded with fuel. And the fuel itself accounts for about 3,400 tons.
Yeah, that's about 7 million pounds in freedom unit. So Also, like historically, what's happened to these boosters that you shoot it up with a rocket and then you basically disengage it, right? And you just threw it away, if I remember correctly. It's like disposable part of the rocket. You always like throw it away. But it's such a waste when you have like this technology in it, and you maybe there'll be sometimes they just dump the fuel out too, and it just depends on this what situation calls, and it's just a waste. They have to recover it. Might have to basically recycle it, and the fact that we can basically land it back, cache it, is quite a remarkable feat.
Yeah, it helps. I mean, when you detach it, what usually happens? It falls back down to Earth and burns up in the atmosphere, or it gets damaged, or it gets lost in the ocean somewhere. Or sometimes it can, depending on what stage, things can detach and get stuck in the Earth's orbit, adding to space junk. So kind of nice that they can do that now.
So with that, we've actually been recovering rockets since the start of the space shuttle program. So with the space shuttle itself, it had the shuttle orbital vehicle. It had the liquid fuel tank, which was the giant orange one, which was previously white. And then it has the solid rocket boosters on the side. And with those solid rocket boosters, they were actually able to recover them. They landed in the ocean. They had parachutes, so they landed softly. And then they would send a boat out. It would bring it back in. They would restore it so that they could actually use it again. And they're actually still using those solid rocket boosters for the SLS missions. So the SLS is the Space Launch System, which has been in the works for the shuttle replacement kind of for quite a while now. And they've done a couple test flights, but they're actually even more reusing those solid rocket boosters from the shuttle with this system too. However, SpaceX, the company behind Starship and the Falcon 9, which is launching, it seems, a couple times a week now, they've really made history before by having this first stage of the Falcon 9 and the Falcon Heavy as well, which is essentially just 3 Falcon 9s put together. But they've been landing these first stages for about 9 years now. And since their first landing, they've had over 350 successful landings, which of course saves a lot of material. It's not wasteful, but also saves a lot of money. So they're able to bring down the costs. For the space shuttle, it was something like a few $100 million to over $1 billion for a single launch. Whereas nowadays we're down to $50 million for a single launch. And so it's a lot easier to, especially for smaller companies or for research projects or things like that, to launch on these rockets, partly because of this reusability.
And also, it's like it lays the foundation for the future of space exploration to the fact that we can re-land basically almost everything, right? That's the kind of like the idea to basically not keep throwing stuff away or leave it as space junk. So it's like how planes are now, right? Imagine if you have to get on a plane and when you get to destination, you have to throw the plane away. It doesn't really make sense, right? Or some kind of like the launcher for the plane, you need to replace it every time. So I think this is a good step forward, and I'm glad it's in our generation that this is happening, that we can see it live, which is amazing. We have the internet. We can literally watch it live.
How automated is it? You might have said this and I missed it.
I mean, completely automated. And
Oh.
and that's the thing is they have algorithms running within it, which are essentially feedback loops. So it's able to self-correct itself. It's able to self-correct. And so as I mentioned earlier, this was the 5th test flight for the Starship. And again, this super heavy booster, it was able to launch the Starship up to space. Starship eventually controlled land, but it still crash landed in the Indian Ocean. But the Super Heavy came back down to exactly where it launched from. And then these 2 arms, which are have commonly been called chopsticks, were able to catch essentially a 23-story tall building by its grid fins. And those grid fins have to be strong. They're strong anyway, so they're a good contact point. But those grid fins are used for supersonic maneuvering of the vehicle itself. And part of the reason for the catching, especially by the grid fins, they have good support with grid fins. But then you also save weight with landing gear, because something this large needs very significant landing gear. So if you don't need that, you save tons and tons of weight, so you can launch more, or you can use less fuel. But it's truly incredible the that it's able to land in the exact same spot automatically. And of course, it uses vision systems and other guidance systems, but it's all there's no human intervention there.
Yeah, the videos like from many angles quite impressive too. Some people make the joke of like, you play in reverse, it's just like going up a little bit, but like not as straight up. But like, oh yeah, they fake with the video of the catch just by playing the launch in reverse. But that's kind of funny. But like it's really smooth.
So if you many years from now, when humans live across our solar system, this is how you would you lift off in your rocket ship. And I guess now they're catching like the discarded fuel tanks, but you could imagine maybe they can actually catch rockets and use them to catch rockets with people on them and stuff on other planets. And if we got a base on Mars, you can send some people over and it gets caught on its landing there, and that's kind of cool.
I mean, this was actually something floated by SpaceX, was rapid worldwide transit, pretty much.
Yeah.
So they'd be able to launch these starships and then just have them on a suborbital trajectory, caught in just off the coast of somewhere, and then you just take a boat in, and then they're ready to go for the next set of people by the time the boat comes back with the full load of people. So instead of waiting and say taking a flight out to Eastern Asia, which takes quite a long time, as Feely can vouch for, you can just take like an hour or two, if that, to get there.
A lot of fuel, though. It feels like, is it like really economic to do that? Like, if you're a billionaire and you don't care about resources or the world, or, well, I guess you care about that kind of stuff, but not. I don't know. I don't want to get political, but anyway, if you're a billionaire and you don't care about the money you have to spend, like, yeah, sure, but is it really economical to be doing 1 hour flights across the world in
Or
rockets?
compared to you could get a video call.
Yeah.
It would be infinitely cheaper.
No, but I mean, it'll be interesting to see where this goes in terms of reusability, because I know their plan is to have rapid turnovers. So, partly, if for some there's earlier videos with the whole Artemis project and launching an orbital space station to the moon, is to have this rapid landing, reassembly, and reattachment and launch for fuel tanks, so that they're able to launch Starship. It can orbit the Earth, and then they can rendezvous with it quite quickly with another Starship that's just filled with fuel, so that they do have enough fuel to get to the moon or Mars or beyond. And just a quick note about another cool thing that we're able to see now, thanks to SpaceX specifically, is the re-entry live. So Feely mentioned that we can see all this stuff because of the internet. But one thing that we couldn't really see with the space shuttle was what its re-entry looked like into the atmosphere, because it couldn't transmit downwards. There's this wall of plasma that's created as you're traveling at tens of thousands of kilometers per hour, just pushing through the atmosphere. It causes a lot of ionization and this plasma to form around the body of the space shuttle, or really any other orbital vehicle in the past. So it can't send a signal down towards the Earth to transmit what's going on in real time. But because SpaceX has their Starlink constellation, it doesn't have to transmit downwards. So we've seen live video from Starship re-entering the atmosphere that's essentially being transmitted upwards towards these Starlink satellites that then can get a pretty much live feed of what's going on during re-entry, which is just super cool. And it's able to go upwards because there's not really plasma there. It's just under the spacecraft itself.
Yeah, the aerospace engineers must be like frothing at the mouth having access to those videos, because I bet they can learn a lot from them.
Absolutely.
I mean, they had before, but it was just in live, right? And now the fact that we have the satellites, which the Starlink itself is quite impressive too. Some of my friends had it when they go up to like the rural place in the woods, right? They just take this little box, and then you have the internet that is quite fast. It's in a sense crazy now that we basically have, well, theoretically you could have internet everywhere now if this basically Starlink goes up globally.
Yeah, well, there's a lot of people where I'm from who are using it now because they live in like rural Nova Scotia. Like I have a friend who's had, his internet for the last, I don't know, like most of his life. It's 1 megabit per second or whatever, right? Between him and like three family members in the house, and the ping is like 200 or something, and that's upload. The download's even worse. And so, they try and get better internet, but no companies are willing to come out and install the lines because it costs a ton of money. So they would have to pay it themselves out of pocket. But now they got Starlink for like pretty much the same price as the old internet, and it's 100 megabits per second. It's good internet, low ping. So like, there's art like I have mixed feelings about filling our sky with too many satellites, but at the same time, like it is helping people for sure.
Yeah, no, I've definitely heard some gripes from quite a few astronomers about the interference of these satellites, which there are thousands of now, with astronomy itself. So there are certainly gripes with it, but of course, is it better to have internet provide to everyone worldwide, or is it better to kind of further our understanding of the universe? Which is it's a
Or
hard question to answer.
or
You
trap
could do
ourselves,
both.
or trap ourselves on Earth. That's the other thing with the space garbage. There's that, yeah, we've talked about this before. There's areas of research that are working on cleaning up space junk, and there's areas of research that are now working on how to account for these Starlink satellites and astronomers' data. So it's like people adapt, but yeah, it's an interesting political discussion.
Just on that, it is interesting because Starlink is not designed to last forever. So they have such a low orbit that it will decay in on the order of like a couple of years instead of some space junk that's just orbiting forever. And they are also programmed to essentially retroactively fire a small thruster to burn up in the atmosphere pretty much. And there was an event a couple of years ago where there was a massive solar storm, which caused a thickening of the atmosphere way high up and caused the loss of several of these Starlink satellites because of that thickening. So they were slowing down quite a lot faster and eventually just burned up in the atmosphere because of that.
Yeah, so they're designed to, like, because you wonder, like, if they start crashing on cities and stuff, will they burn up before they hit it, or will little pieces of junk? This is all stuff I'm sure that they like accounted for when designing. But often you can't account for everything, right? Like things go wrong sometimes. So I feel like it's a slippery slope just putting a ton of satellites in the atmosphere, and then you have to argue like, well, like, these satellites are over other countries all the time. Like, you get into like kind of border disputes and things. It's like, who owns the atmosphere? No, right? Like, it's
Yeah,
uh,
it's kind of nice though that has limited lifetime because like now we can basically send in an update, right? Upgraded version of these satellites, and maybe we have better technologies. It's like a update cycle for for the internet.
yeah, that's a really important feature. I think that they designed them to burn up in the atmosphere, and they designed them to be in that like low orbit so that they're not just going to get stuck up there.
So just moving on, just with the interest of time, there is one other thing I want to mention that happened today, and that's another very exciting launch, also by SpaceX. But in this case, this is a more established rocket, the Falcon Heavy. So again, the Falcon Heavy is just three Falcon 9s that are strapped together with the payload on top. But it's designed to launch things either into geostationary orbit for heavy objects or further afield. And just today, from what I can tell, it successfully happened. But we saw the launch of the Clipper mission. And the Clipper mission is very exciting because it's a NASA run probe that will explore Jupiter's moon Europa to search for the possibility of life beyond Earth. There's a really good video on this, I believe, by Real Engineering that goes into detail about the different instruments and kind of how they're able to account for different things, especially in regions around Jupiter, which don't see a lot of sun. I believe it's about 4% of the sun that reaches Earth reaches Jupiter, but still solar powered, and it's able to do, I believe, about 50 flybys of Europa at closest approach, as low as 25 kilometers above the surface. And it's designed to pass by over certain areas and take different data to see, okay, what is underneath the ice? What's the ice composed of? And is there a possibility of life on a moon of Jupiter?
Yeah, they say they're gonna do around 50 flybys and use basically radar to penetrate the ice to see if there's what's in the water under the surface. And when we say life, I don't think they mean the walking aliens or the typical Hollywood movie aliens. Well, it could be just microorganisms or bacteria or some kind of prokaryotes, one cell organism, or even if there's something like cells, maybe they're quite different. Maybe the form is different. But it's gonna be quite a achievement if there's something because like is life is life on Earth the only appropriate form of life that's possible, or are there any other forms that look vastly different but still life? Because in a sense, we only have the sample size of one, which is Earth. So even though we posit those theories that life could come from, in different form and shapes and structures, we haven't seen one. But if the life we find, if we will find any on other moons or planets, have the same structure, it could reinforce the argument that life only comes in this form. But who knows?
Yeah, it's like, could you find non-carbon based life, right? That would be pretty wild. How long does it take to get to Europa?
So this is something I want to talk about just briefly. Is they actually had to change the plan for this mission. So the original launch for this mission was supposed to use the Space Launch System and the Ares 5 rocket, I think it's called. And that's a very large rocket, similar in size to Starship, and it would have taken, I think, under 3 years to get there. But because of delays with that program, and they're still testing it out, and there's a lot of things going on with it, it was launched on this Falcon Heavy instead, and it's expected to reach Jupiter in April 2030. So it will be traveling for just under 6 years, but will travel for a total of 2.8 billion kilometers in a less direct route, but a more fuel efficient route. And also, the one other interesting fact about this is both this probe and Cassini, they're both solar powered, which kind of doesn't make sense just because you're so far away from the sun, you get so little energy. So the solar panels that they have to have are quite large. And again, the original plan was to use some sort of radioactive isotope in order to power the instrument, like what we see on the Curiosity and Perseverance rovers, and with other interplanetary probes, and I guess now interstellar probes. But because the US isn't really manufacturing nuclear weapons anymore after the nuclear test ban treaty and all of the Cold War stuff, they're in such short supply that they don't want to use it for this mission. So for the past couple missions that have gone out to these gas giants, they've been forced to use solar panels, which I just find very interesting.
Did they use that like I read, maybe we even talked about this, that they use this like origami techniques to like more efficiently fold solar panels in these things. I don't know if we talked about that or not. That we should if we haven't.
I think this one uses kind of a more traditional, just simple folding, but there's very interesting origami that goes into the magnetometer setup because it's this very long pole that just kind of spins and unfolds itself and actually houses 3 magnetometers in the 3 different orientations along a 3D axis. And that uses some cool folding techniques, but the solar panels themselves are a lot simpler compared to something like, say, the James Webb Space Telescope.
All right. With that interesting bit and pieces of news, it seems like even though they're launching stuff now, sometimes it takes years to get results and see something of it. We still analyze data we got from launches decades ago, right? So it's an interesting time, but it's also, we need a lot of patience for this type of discovery. Well, moving on to our main topic, which is the Nobel Prize in Physics was announced. Oh, exciting news, right? I think this one is a little more controversial than usual. When woke up, I got an email from CAP, I think, yeah, Canadian Association of Physicists. Basically, they also announced the news through the email list. And also the American Physical Society, APS, also announced to it. And since I'm part of the DSOFT and Division of Soft Matter, and also the GSNP, the statistical physics thing, they also announced that too. Because in a sense, well, it is a statistical physics, applied statistical physics. So that, in a way, to me, is kind of close to my field, but somehow it doesn't feel too much like physics either. Some people would disagree with me. I know that. Like, oh, I think we had a lengthy discussion at work or in my department among my colleagues and friends about it. Like, oh, what do we think about these?
So who won it and what was it for?
Patrick, you want to hop on that?
Yeah. So for the Nobel Prize itself, it was won by um, John Hopfield and Geoffrey Hinton. So Hopfield and Hinton were collaborators, and they were kind of working on early examples of how complex computations could emerge from tunable interactions. So they were looking at how you can essentially input parameters into an algorithm and have it in a feedback loop. And we've talked about feedback loops before, even earlier in the episode for landing rockets. But they were looking at how they could do this with what are known as Boltzmann machines with hidden units. So these were ways in which you could kind of expand modeling data by really examining, okay, what variables within, say, an algorithm can we tune? And more importantly, how can we self-tune those algorithms? So to delve into it a little bit more, a Boltzmann machine itself, also known as a Sherrington-Kirkpatrick model, is named after, of course, Boltzmann, who we've talked about many, many times before. And it looks at, in this case, kind of a spin glass model with an external field. Now, a spin glass model, someone might be able to chime in with a bit more information on that, but it's essentially a spin glass itself is a magnetic state characterized by randomness, and doesn't really take into account cooperative behavior in freezing the spins. And so, for example, for ferromagnetic solids, the magnetic spins all align, but within the spin glass, it's not all aligned. It's just these kind of random orientations of spins. So they were originally looking at this, and for Boltzmann machines themselves, they're interesting because of locality and they're kind of heavy in nature. And so this is kind of the idea where this training algorithm comes into place of trying to see, okay, when we input these different parameters, how are they responding? And then how are they being tuned, or how are they essentially being oriented in a way based on an input and an output?
Well, the point of this was to study the brain, basically, right? If you can have, well, it's a stochastic Ising model. So with, I think, tunable interactions. What it means is basically what Patrick said. You have a network of something, like, things are connected certain way, but you want to be able to tune the strength of those connections, or study the system where the strength of the interaction changes by certain laws, rules, or maybe it's random or something like that. And what ended up being used for in the very recently is to study the or to use for the artificial intelligence and machine learning. Even though the purpose when it first started is to study the behavior of the brain, so this is the part I was saying, is used very clever statistical method, like in statistical physics, to try to envelop this problem and solve in the physics term per se, to give some kind of understanding of how these system evolve and how these system behave.
Yeah. So we've talked about machine learning a bit. I believe it was, forget the episode number, but it's the mysteries of machine learning, which you can find in the show notes. But just as a bit of background, that one, they were just trying to find ways in which they could automate this process of essentially creating these networks or these programs that are able to self-reference and self-check themselves. And so for the basis itself of a neural network, because these were based on the brain, is what's known as a perceptron. And this perceptron is essentially a node within an algorithm that has some sort of function describing it. So if we just take the example of, for example, a perceptron which is linear, so you have an input, let's just say, call it x. You input it. The function of this perceptron is linear, so you map x to some sort of y value, and that will output the y value. So in this very simple case, just a linear equation with the input being x, the output being y, and then the function itself being the perceptron can be modeled by a perceptron. But in this case, what you want to do is be able to have the perceptron reconfigure itself or adjust the function in such a way that if you put x and then you're expecting an output y, you can say, okay, we're expecting this y based on x. Readjust yourself so that you get closer. And of course, it's not typically linear, especially nowadays. They tend to be some sort of sigmoid function where you have values between 0 and 1, and there's some level between them that indicates essentially the perceptron's level of confidence. And then when you have many of these in a row, and what are known as hidden layers, this begins to form a neural network because each perceptron takes in the input from all other components of the layers beforehand. So if you have one input, it will be fed to, say, 5 perceptrons in the first hidden layer. Then the output from each of those perceptrons is sent to 5 others. So there's this network taking place where they're all kind of interacting with each other, relying on each other, much like neurons in the brain. And then all will output one value or one expected number, or again, some sort of value. And they'll also be able to provide something like the certainty or the confidence in which they are in predicting that value. And so with that, of course, for very large neural networks, you need a lot of training data and you need a lot of validation data to make sure that everything has been trained right and those parameters have been tweaked in such a way that it will be correct given a certain data set.
So where has this? Because I won the Nobel Prize, which typically means that this stuff is being used right now in the world to solve problems, right? That's kind of typically how the Nobel Prize works, I thought.
Not really. Oh, well, what is neutrino mixing using for?
Good point. Well, all right, fair enough. They yeah, okay, they discovered that neutrinos have mass, so they've proved something, I guess. So what did they developed these
It's a
algorithms?
breakthrough scientific discovery, right? And I think part of it is how applicable it is. And
Mhm.
I don't think it's that big of a part, but I think how important the breakthrough is. And as we can see, like the understanding the brain is one of the biggest mystery that we have.
Mhm.
And it just turned out that if we create an artificial system that basically mimic how neural network works, is able to perform like a tiny brain, right? because real brain had billions of neurons, but in artificial neural networks, we have much smaller number. But to be able to understand that, we need to understand how these type of more abstract system evolve and behave. What if we tune the interaction this way? How does this work? Is there equilibrium in the system? Is there something like a phase transition, a critical point? Something like in this physics term, it's kind of help us formulate understanding and basic knowledge of how these networks work.
Yeah, so I think it's cool. So like the controversial stuff is that this is mostly math and computer science, but I guess at the very basic level, it's kind of like a many-body physics problem, where you have a bunch of things and they interact with each other in certain ways, and it's really complicated. But there's ways around it using these kind of algorithms and tricks and self-correcting things, which is far beyond me. So yeah, it's cool that they're like a lot of people when they first like I was reading about this too, Feely, when it came out, and I haven't read too much on it, but most of the people in comment sections were just like, "This isn't physics, like this is math and computer science, like what the heck?" And like I can kind of see that argument, but it's also the ideas there. I don't know, like I don't know what the right answer is, because it's basically just a many body physics problem. Thinking about the brain like like a many body system, it's not new, and that's why they won the Nobel Prize for it, right? They've been doing it for a long time, but lots of people do it. Like even at our old university, one of our old profs was doing like brain statistical mechanics, and I thought that was really cool. I didn't understand much of it, but I thought it was great. So yeah, it's we'll probably talk more about that controversy stuff in a minute, but Patrick.
Yeah, I mean, I think just to settle some of that controversy, it's important to look at exactly the research that each of these individuals did. So again, it's John Hopfield and Geoffrey Hinton, and Hinton is Canadian, right?
Woo.
Or based in Canada.
He might have like
he's at U of T.
Yeah.
Yeah,
So
I think he
kind
might
of
be
Canadian.
British. He's like dual. He's like British, moved to Canada, maybe.
I believe he's actually American and then moved to Canada.
Let me look this up.
But we might hear more about that in our story later today.
Well, I think one thing that kind of when I first heard about this, I think the way they phrase it in the Nobel Prize announcement is that for the discovery that enables artificial neural networks, right, or artificial intelligence. So the focus seemed to be on the artificial intelligence part, but the work is enables artificial intelligence because they don't exactly do artificial intelligence exactly.
Yeah. So I do just want to spend a minute talking about what each of them did specifically. So we did kind of talk about the Boltzmann machine, which was more the focus of Geoffrey Hinton. So in this case, it was using statistical physics in its essence to try and trade by feeding examples to this system to try and identify images or create new examples of the type of pattern of which it was trained. So, of course, this is more generalized to neural networks. But for the work of Hinton, it was, of course, based on statistical physics and really just trying to find lower energy states.
So Geoffrey Hinton is British Canadian, and John Hopfield is Polish American.
Very cool.
Just before I forget.
But for John Hopfield himself, looking at the work he did, and especially his Hopfield network, of which it's named after, he was trying to come up with these different systems and ways in which they can be represented. So for Hopfield, he was looking at how we can save and recreate patterns and imagined these different nodes as individual pixels. And so he was able to utilize physics that describes a material's characteristics due to its spin. So kind of going back to that magnetism and the Boltzmann machine. But by looking at how you can put in a network of random distributions, or I guess random values, which he associated with spins, and then by training it to find connections. So in the work of John Hopfield, it wasn't so much of, okay, we're looking at an input, we're trying to get an output, let's work back and forth within the algorithm to see how we can tweak those parameters. Instead, it was looking at the interactions of those parameters themselves. So the models he developed were trained to find values between the connections or the pixels or the nodes or however you want to call them, so that the saved images themselves are at their essentially lowest energy state. So when a Hopfield network is fed, say, a distorted or an incomplete image, whether, again, that's accounting for spins, they're just some sort of quantity represented by pixels, it's able to methodically work through these pixels, see how they're related, and then update their value such that it minimizes the energy in whatever way that the energy is defined. So in this case, I would say more so than work towards neural networks, which it certainly did provide the basis for in terms of interactions between pixels and trying to fill in the space and looking at how we can actually train and tweak these values. It's more so just computational statistical physics, where it's looking at how we can develop these self-referential networks to minimize energy, which, I mean, there are probably many different ways in which you can say that for machine learning and how machine learning algorithms use it. But in a physics sense, it's looking at how we can reference and tweak parameters to minimize energy while maximizing, in this case, say, an output or finding an ideal output.
Well, I was reading the email where the topical group of statistical and nonlinear physics sent me, and there was this quote that's interesting. I'd like to read. So, according to it's from David Schwab and Yuhai Tu, which is a longtime co-organizers of the March meetings in the U.S. So they were talking on the statistical physics meets machine learning, and I quote. Hopfield networks were an early example of how complex computations could emerge from tunable interactions among relatively simple components in a controllable fashion. Hinton and collaborators generalized Hopfield networks to Boltzmann's machines with hidden units, expanding the power of pairwise interactions for modeling data. While these systems can be considered a new form of complex adaptive matter, leveraging concepts of energy, disorder, dynamics, and equilibrium from statistical physics. Hopfield and Hinton's motivation was to understand the brain. By searching for simple principles of learning in complex systems, they and others led us down a path to the models and understanding we have today for a wide variety of physical and computational systems. End quote. So I think it's put me a little more of this perspective that, it's really not about artificial intelligence, really. Artificial intelligence, it just turned out to be one use case of this kind of tunable complex system, because you could imagine some type of a natural material that have like a tunable interactions, or maybe doped with some things that can change interactions and how to understand those systems, and perhaps it appeared that the brain appears to be one of those type of systems, and that we can model using it. So that's why I find like the phrasing of the announcement makes it much more on the artificial intelligence, which when you see their research and their studies, I don't think is emphasizes, like the emphasis is not on artificial intelligence, it's just on this type of complex system that are adaptable, right? Like have basically like this kind of adaptive interactions which could have many applications, and in a sense a little bit close to my view of it. I was like, ooh, get a little, it's nice to have the recognition in statistical physics, because it's been a while since like theoretical statistical physics has been in the limelight, I think, which is nice to have.
Yes. theoretical statistical physics is a deep thing, so I think it's tricky for a lot of people. But yeah, like, they emphasized artificial intelligence, but I bet the material, like the solid state condensed matter people have been using this kind of stuff for a while now, because again, it's just a many body physics problem, and this is the beauty of physics for me, is taking something complicated and trying to like break it down into this minimal model. You look at a brain's pretty complicated. There's a lot going on, but they've said, like, all right, if we care about information and artificial intelligence, how do we conceptualize, like, how do we model a brain? And you can do that with like many body kind of this many body interaction thought process. So I really like that, actually, that's kind of the physics going on behind it. And yeah, like, I think as time goes on, all those people who were complaining at first might realize, or the ones who actually go do their research will realize, like, okay, it's a physics problem. And often, as the case the case that often happens with physics problems is that they have way more applications than you realize. um Yeah, like assuming something is a sphere, turns out it's really useful in many different situations, probably not just the original situation it was intended for. And same with this neural network stuff. Maybe it was originally developed for these tunable interactions. Turns out you can use that for all kinds of other things too. And I'm sure you can use it for, like, when you say neural network, you don't have to be talking about the brain. Neural networks show up in a lot of other places. They show up in like um modeling like connections on the internet and all kinds of things. So
So, with all this being said, I know we talked about in our last episode kind of who we might expect or what field we might expect to win the Nobel Prize in physics this year. Uh, Liam, you most notably said that you think Barry was very deserving of it. And of course, I mean, we were kind of due for something in quantum mechanics and like kind of
condensed matter.
that
So
condensed matter.
this
And
is like
yeah,
it was like condensed matter, statistical mechanics. So it hit the mark partially.
okay. But not satisfied until Barry wins it.
Well, if he wins it, my career becomes easier because he was my supervisor's supervisor. So I can say my grand supervisor won a Nobel Prize. Now he definitely deserves one. He's done a lot. But I'm a little biased. I would really like him to win one because then I can tell people that.
Well, the other thing that put icing on the cake for this year's Nobel winners is also the Nobel Prize in Chemistry, which is also have AI in it. So is maybe Skynet is on the committee, but like is
Ah,
the artificial intelligence is taking over. So the Nobel Prize in Chemistry is awarded for the prediction of protein structure, I think, and because proteins basically made of a bunch of amino acids, right? And they form structures that are useful in our daily life, in organic matter and whatnot. I don't know too much about it, but protein folding is one of the mystery of life is really hard to figure out. And I think they found a way to predict protein structure or find novel protein structures using their algorithm and their basically machine learning thingy.
Yeah, it's really interesting how the prize has been split because it does both focus on proteins, and it's also interesting how recent some of the research is. Because sometimes, especially in physics, we see like 40, 50-year-old research. But in this case, the work of David Baker, who won half the prize, his work was done in 2003, which succeeded in using the building blocks of proteins, amino acids, to build essentially brand new proteins that had never been seen before. And so he was actually able to use the research that he did based on the 20 different amino acids that make up all proteins that we know of to be used in different ways. So he was actually able to form proteins to create different things that were beneficial for pharmaceuticals, for vaccines, nanomaterials, even tiny sensors. Now, the other half of the award was split between two people. That's Demis Hassabis and John Jumper, who did their work in 2020. So only 4 years ago,
wow.
when they presented their AI model, which was called AlphaFold 2, And of course, it's AI related, but it's essentially able to predict the structure of all the proteins that researchers have identified. So it's able to use this algorithm that's been trained, like what we talked before, and it's able to essentially accurately identify how these about 200 million different proteins are able to fold. And so, since this breakthrough, that's huge for medicine because by knowing how proteins fold or by knowing their shape and their structure, we are better able to understand how to deal with them, whether that's something like a prion disease, which is essentially a think mad cow disease, for example, where prions cause other proteins to misfold. And then it's just this chain reaction that grows and grows as more and more proteins become misfolded. And so that's a very big medical problem. And so by understanding, just say, okay, we input these amino acids in this chain, how are they going to fold? And how would they react if we made changes to them? So by understanding that and creating this AI model, they were able to advance knowledge about protein structures by just a ton. And it's being used by so many different people in the health sciences and in research and in medicine. So it's really quite incredible what the extent of their algorithm, as well as its uses in especially medicine.
The stars like might have aligned for them because you said it was in 2020 they developed it, and that was right during COVID, right? And there was a lot of money going into health research and whatnot during that time, so that might have helped speed up the process of them getting the Nobel Prize partially. But this could be the beginning of a trend, right? Like, I bet, Nobel Prizes in the coming years, there's going to be a lot of artificial intelligence sprinkled in there, I think. Because it's just so powerful, right? Like, it's crazy how powerful it is.
For sure. And just looking at the paper, so it was published in Nature, which makes sense. But it was published July 15th, 2021, which is just wild. The fact that there's a 3-year-old paper that has now won the Nobel Prize. I mean, you rarely see that in a field nowadays.
Well, the work that the Physics Nobel Prize was given for was done in like the 80s or something, right? Like,
Mhm.
so they're just getting it in 2024, and it was for work in the 80s, and that's like pretty common in Nobel Prize land.
Yeah, I mean, it's a huge application. It's very impactful application too. It's the one that's like on the press release, like understand the antibiotic resistance and create images of enzymes that can decompose plastic. And like either of those things are massive impact in itself. One thing to me that I was reading through to their work, I was like, "Ooh, man, this is uncannily similar to what I'm trying to do for my research basically, but not with AI, not with protein, but the goal is similar because they try to understand how protein form. I'm trying to understand how nanostructures form, and we're working at a similar scale, but a little different. But and they seem to have their stuff figured out. I still trying to figure out my stuff. So but very interesting to see. In a sense, this also like a statistical physics too. Like people use statistical physics to try to understand protein folding for a long time because there are these two type of entropies that's in play in the folding, like configurational and conformational entropy, and blah 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 blah. All this boring details, but it's very complicated. And the fact that they can do this, oh, also fortunately, protein has and lots of data that they can crawl through to create to train their system. In contrast to I don't know what I'm trying to do, which is also a little messy right now. So,
Yeah, I
but
think
it's interesting to see.
it's a well-known thing, I think, that you can maybe at like a super basic level and not realistic level, but you can try and understand protein foldings through like energy minimization and entropy and that kind of stuff. So yeah, so it's cool that physics and chemistry kind of went to statistical mechanics fields, although they were kind of masked by other things, artificial intelligence and health science. I mean, like, they're huge in those fields, right? So it makes sense. But yeah, I'm not sure if Patrick, you have anything else you want to say on it, or any of the other Nobel Prizes, or I have another one to mention before we get to the story later.
Yes. So one thing I just want to mention is we're very fortunate in the physics department at the University of Alberta to have Dr. Michael Woodside, who focuses on how proteins fold and the energy related to that folding by using laser tweezers, which I would love to get one of his students on someday. He's excellent to talk to. But the other Nobel Prize I would like to mention is, of course, the Nobel Prize in Medicine and Physiology. So this kind of relates to the micro world as well, kind of with proteins, but it's went to Victor Ambros and Gary Ruvkin for the discovery of microRNA, or ribonucleic acid, and its role in post-transcriptional gene regulation. And so essentially mRNA, that's actually a common word nowadays because we have mRNA vaccines, such as the COVID vaccine, and there are more and more coming out. But messenger RNA, or microRNA, I should say, is the RNA, or the ribonucleic acid that's found within cells that is actually responsible for building proteins within your cells. So you have your DNA, and of course, all your cells have the same DNA, but when they're transcribed to RNA, which is, I always learned it as messenger RNA. Apparently, microRNA is also the word. So that's actually able to be sent out into the cell, attached to certain enzymes, and then proteins are built from that. And it's really interesting because they found out that because of mRNA, this transcription to translation process, where it goes from DNA to mRNA to a protein, essentially the way in which mRNA is produced and which parts of the DNA it's transcribing will affect the cell type. So when the mRNA looks at different parts of the genome within DNA and at different genes, it's able to transcribe some, but not others within a cell, which then leads to the cell specialization. So I think we've mentioned stem cells before, but this is how stem cells can become, say, nerve cells or muscle cells or skin cells, or a whole host of different types of cells in your body through the fact that mRNA is responsible for selectively transcribing and translating that to proteins. So I think that's also a very cool field to look into. And I mean, because of the work that they were able to do with mRNA, we now have more effective vaccinations and treatments. And there are a lot of exciting studies going on, especially, for example, with cancer treatment or autoimmune diseases, where they're looking into using mRNA that's developed outside the host body, injected into it, and then that is able to help those cells develop either an immunity, especially for your immune cells, or able to fight back, say, against cancer cells that are maybe not recognizable. So lots of really exciting work that stemmed from that. And of course, a worldwide pandemic was helped slowed because of it. So really, I think, well-deserved Medicine and Physiology Nobel Prize, with much less controversy than the AI-related things.
So one more Nobel Prize I wanted to discuss quickly is the Ig-Nobel Prize in Physics for 2024. So we've talked about the Ig-Nobel Prizes before, but like a quick summary is that they're kind of like goofy Nobel Prizes. So people did some research and they learned some things, but they're kind of like less serious topics, and they're not necessarily ones that are going to change the world, but it is like original research. They have learned something that no one knew before. So we've talked about it before. I don't remember which episodes. Probably other Nobel Prize episodes. But the 2024 Ig Nobel Prize in Physics, it was awarded, I think, in like mid-September. And it was awarded to James Liao, or Liao. Not quite sure exactly how to pronounce that. But he works at Academia Sinica in Taiwan, and he was able to explain the swimming abilities of dead trout. So he says, quote, "I discovered that a live fish moved more than a dead fish, but not by much. A dead trout towed behind a stick also flaps its tail to the beat of the current like a live fish surfing on swirling eddies, recapturing the energy in its environment. A dead fish does live fish things." End quote. So this work won him the Ig Nobel Prize, and this was work that he published in 2004 in the Journal of Experimental Biology that was titled Neuromuscular Control of Trout Swimming in a Vortex Street, Implications for Energy Economy During the Kármán Gate. So, in the abstract of the paper, it says that when exposed to vortices shed from a cylinder, fishes hold station by adopting a mode of locomotion called Kármán Gate, where the body of the fish displays large lateral oscillations and the tail beat frequency matches the vortex shedding frequency of the cylinder. Although field studies indicate that fishes often prefer turbulent flows over uniform currents, the effect of hydrodynamic perturbations on the mechanics, control, and energetics of locomotion is still poorly understood. So basically, kind of to, dumb down what he said, turns out that fish evolved so that they're more energy efficient. So their bodies kind of automatically react to the currents in rivers, for example, or ocean. I guess trout or river fish, right? Are they? I don't know. Okay. Yes.
Freshwater fish.
Can be.
Yeah. So you get like certain vortices that form from the edges and rivers, and the trout evolve such that their bodies kind of automatically flap with the frequency of these so that they don't actually have to engage their muscles near as much to keep going. So people noticed in the past that if there was that you would put a dead trout in the water, it would still look like it was swimming and it would still move forward, which is kind of wild. So that was the 2024 Ig Nobel Prize in Physics award, because it's kind of goofy, but it's also like a very interesting thing that they've learned, and could have applications. You can imagine people design things that go in water with these specific shapes that will move in frequency in tandem with the frequency of vortices.
Like bait, right?
Yeah.
It's like big fish to bait to get all the fish.
Yeah, exactly, right? Or like, robots that go underwater or are meant to go up rivers, or who knows, right? A lot of this stuff you don't realize the application until people think of ideas they're like, oh, I could improve my design by making it like this. You could use biomimicry.
Ooh.
Throwback.
I do just want to throw out one open question. Does not require an answer, but do fish experience rigor mortis? And then the other comment I just want to say is that with the Ig Nobel Prize, it's actually quite well known, and there's been exactly one person who has won both the Ig Nobel Prize and the Nobel Prize, and that's Sir Andrew Geim, who was awarded the Ig Nobel Prize in 2000 for levitating a frog by magnetism, but he was also awarded the actual Nobel Prize in Physics in 2010 for his work on graphene.
And he co-won that Ig Nobel Prize with Michael Berry. So if Michael Berry won the Nobel Prize, then he would be the second person, and they would both share the same Ig Nobel Prize. So I really want Michael Berry to win. It's like personal reasons, 50%, but it would be awesome, wouldn't it? That frog levitation magnet Ig Nobel Prize, him and Michael Berry co-won it. I'm not sure. I honestly don't know who did what in that, like who contributed what, but they both won it, so they both contributed something.
Amazing.
Well, from my brief look, it looks like also rigor mortis also settles in fish.
Good to know.
I don't know why you want to know that.
Yeah, but probably not that much. But yeah, I think it's the entire topic on how it settles, right? Like a body produce ATP and blah blah blah, with like this calcium deposit.
Yeah.
I don't know too much about it. I'm sure someone we know probably know about it. But well, I guess that's the main topic for today. And before we move on to the story by Patrick, we gotta get Patrick to tell us how to reach us.
Yeah. So for reaching us, there are many different ways in which you can reach out. If you have questions about this episode, if you want to find out more information, or if you want to be a guest on this show. So the best way to reach us is through email. We are hyperthesispodcast@gmail.com. So you can send us an email with questions, or we can, well, again, we would love to have you as a guest. Whatever you do in science, whatever your field of expertise, we would love to have you on the show and ask you questions about your research and just learn about what you do. So it could be physics, it could be chemistry, it could be earth science, it could be medicine, really anything. We would love to pick your brain live on the air, although I guess not live. So you can send us an email over at hyperthesispodcast@gmail.com, linked in the show notes. You can also find us on Instagram and send us a DM, or you can just follow us and like our posts. We'll be sending out updates. We have been off for a little bit of a break, and we're still recording during our break. So you can figure out what we've been up to and when we're back, which will hopefully be quite soon. You're already listening to this, so we're already back with our 7th season, I think we agreed on. So you can reach out to us there. And you can also check out our Instagram, possibly for some spicy memes or for some other physics news, because there's so much going on in both physics and science that we really want to share as much as we can, ideally. Yeah, if you are listening to us, congratulations, you found us. But we are on pretty much wherever you can find your podcasts, whether it's on Spotify, which we're based out of, or you can find us on YouTube Music, Apple Podcast, Audible. Really, wherever you find your podcasts, you can find the Hyperthesis. Finally, we are on YouTube. We are up to date up to season 6, and hopefully by the time this is uploaded, we might have some of our season 7 episodes uploaded as well. And maybe, who knows, we'll try and get those concurrent, depending on the ability of Feely to use his nice MacBook for the processing. So whether you have questions about something we talked about, you have comments about what you would like to hear in a future episode, or you are an expert in your field, we would love to have you on. Feel free to get in touch with us, share us, give us a rating, comments, whatever you can do to interact with us. And thanks for listening.
And now to the story.
Hello, everybody. My name's Patrick, and I'll be telling the story today. No, I'm just calling out Feely for getting the names wrong earlier. I'm doing the story.
I thought Patrick was doing it. I guess you.
Yeah, that's all right. So today's story, because it's me doing it, not Patrick, the quality will be about 50% of what it usually is, and it'll be about 50% as long. So it's a little short story. It's just kind of some background information on our 2 Physics Nobel Prize winners, John Hopfield and Geoffrey Hinton. So I'll start with John. And John Hopfield, so he was born in 1933 in Chicago to physicist. His dad's name was, conveniently enough, John Hopfield as well, and his mom's name was Helen Hopfield. So both of his parents were actually physicists, apparently. So he had a nice little jump start on his academic career, probably. He could learn from his parents' mistakes as well as his own. He received his Bachelor of Arts with major in physics from Swarthmore College in Pennsylvania in 1954, and his PhD in physics he received from Cornell University in 1958, where his thesis was titled A Quantum Mechanical Theory of the Contribution of Excitons to the Complex Dielectric Constant of Crystals, under the supervision of Albert Overhauser, if I pronounced that right. He went on to work for 2 years in the theory group at Bell Laboratories on the optics of semiconductors, and later on he worked towards a model to describe the behavior of hemoglobin. So kind of a few different fields in his earlier years. And he later became a faculty member at the University of California for a few years, and then Princeton University for about 16 years. Then the California Institute of Technology as a chemistry prof for 17 years, and then back to Princeton from 1997 until current day, where he has been a prof since, and now he's a retired molecular biology professor. Fun fact, from 1981 to 1983, Hopfield taught a 1-year course at Caltech called The Physics of Computation, alongside Richard Feynman and another physicist whose name I couldn't find. So Feynman actually invited Hopfield to teach about associative neural networks, and this collaboration actually inspired the Computation in Neural Systems PhD program at Caltech that was founded in 1986. So he was buddies with Richard Feynman, apparently, or at least colleagues. So that's just a little bit of background information on John Hopfield, and a little bit on Geoffrey Hinton. So Geoffrey Hinton, born December 6, 1947, is a British-Canadian computer scientist, cognitive psychologist, and he's known for his work on artificial neural networks. And sometimes he's apparently called the godfather of AI for his experience and knowledge on the subject. So he really knows what he's talking about, apparently, to get a title like that. He received his undergraduate education at both Clifton College in Bristol, the United Kingdom, and the University of Cambridge. After repeatedly changing between what degree he wanted to do, he kind of hopped between different subjects, like natural sciences, history of art, philosophy. He actually graduated in 1970 with a Bachelor of Arts degree in experimental psychology and continued to study at the University of Edinburgh, where he was awarded a PhD in artificial intelligence in 1978. So I didn't realize they would do a PhD in artificial intelligence that early because it was kind of a new and up-and-coming field. But he did this under the supervision of Christopher Longet Higgins. I might have pronounced that wrong as well. After his PhD, Hinton he worked at the University of Sussex and at the MRC Applied Psychology Unit. Then he moved to the University of California, and then he moved to the Carnegie Mellon University. He's currently a retired professor in computer science at the department, in the computer science department at the University of Toronto. So pretty close to me, fairly close to Feely, a bit farther from Patrick, but in Canada. So that's, whenever a Canadian wins a Nobel Prize, it's always a win for the three of us. And he's been affiliated there since 1987. When Hinton arrived in Canada, he was appointed to the Canadian Institute for Advanced Research, which sometimes is called CIFAR. I don't know, CIFAR, they might pronounce it. In 1987, as a fellow in their first research program on artificial intelligence, robotics, and society. And with his help, CIFAR launched the Neural Computation and Adaptive Perception Program, which today is named the Learning in Machines and Brains Program, which he led for 10 years. And in 2018, along with his colleagues, Hinton won the Turing Award for his contribution. So the Turing Award's kind of like, is it like the Nobel Prize of computer science?
Something like that, yeah.
Yeah, so it's a very important award in kind of computer science, I believe. So he won that before he won the Nobel Prize. So those are two major prizes under his belt. So Hinton's fun fact is that his middle name is Everest, because apparently one of his cousins or one of his distant relatives actually was the one who Mount Everest is named after. And then a second fun fact is that he is the great-great-grandson of the mathematician and educator Mary Everest Boole and her husband, George Boole. George Boole's work eventually became one of the foundations of modern computer science. You've heard of Boolean algebra. I think we've talked about it. So it's kind of fitting that he went on to do kind of like artificial intelligence, computer stuff, and win a Nobel Prize when his great-great-grandfather was Boole himself. So I thought that was kind of neat. And that's some background information on our two Physics Nobel Prize winners this year.
All right, thank you, Liam, for the story of the Nobel laureates this year. Well, it looks like it's time, so I will say goodbye here, and I will catch everyone next week. Take care.
Bye, everyone.
See ya.